Welcome to Mindful Moments. Nourish your mind on the go. This audio uses AI narration to present our original book analysis. Today, we're diving deep into Stephen Hawking's A Brief History of Time, a book that tackles some of the biggest questions about our universe. You'll get the key insights without having to wade through the complex physics.
Yeah, it's a book that truly captures the imagination and makes you think about our place in the cosmos in a whole new way.
Okay, so let's unpack this. Hawking starts by taking us way back to the ancient Greeks and how they viewed the universe. It's amazing how Aristotle figured out the Earth was round back in 340 BC without any of the tools we have today. It makes you realize how much we can figure out just by observing the world around us.
Aristotle's deduction was based on simple observations, like the Earth's round shadow during a lunar eclipse and the changing position of the North Star as you travel south. What's remarkable is that these simple observations, available to anyone who pays attention, led to such a profound understanding of our planet's shape.
It really shows the power of human curiosity and observation, doesn't it? But of course, they didn't get everything right. The Ptolemaic model, with the Earth at the center, was accepted for centuries, even though it had its flaws.
Right, the Ptolemaic model, while a good first attempt, it couldn't fully account for things like the moon's apparent size in the sky. Then Copernicus comes along and shakes things up with his heliocentric model, placing the sun at the center. It was a revolutionary idea, but it was Galileo who really championed it and provided observational evidence.
You're right. Galileo's observations of Venus's phases were a major blow to the Earth-centered model. This really highlights how science progresses by constantly questioning and refining our understanding. And then comes Newton, who brings us his laws of motion and universal gravitation, giving us a framework to understand how objects move and interact, not just on Earth, but throughout the universe.
It's like suddenly we had this new set of rules to explain the cosmic dance of planets and stars.
But even Newton's theories weren't the final word, right? That's where Einstein and his theory of relativity come in, completely changing our understanding of space and time.
Einstein's theory of relativity is truly groundbreaking. It shows us that space and time are intertwined, forming a fabric called space-time. This fabric can be warped and curved by mass and energy, meaning our perception of space and time is not absolute, but depends on our frame of reference.
So it's not just what we measure, but how our perspective as the observer changes things. This has massive implications for our understanding of gravity, the speed of light, and even the evolution of the universe. For example, Einstein showed that gravity isn't a force acting at a distance, but rather a consequence of the curvature of space-time, like a bowling ball on a trampoline.
And because of this curvature, light bends around massive objects. This isn't just theory. We can observe light bending around rotating black holes, confirming Einstein's predictions.
So relativity gives us the tools. But now let's zoom OUT to the biggest scale. The universe itself is changing. Hawking talks about the expanding universe, meaning the entire universe is getting bigger. This leads to one of the biggest questions of all. How did it all begin?
The expanding universe is a fundamental concept in cosmology. Edwin Hubble's observations in the 1920s showed that galaxies are moving away from each other, and the further away they are, the faster they are receding. If we rewind the cosmic film, everything converges to a single point, an incredibly dense and hot beginning the Big Bang.
And we actually have evidence for the Big Bang, in the form of the cosmic microwave background radiation, a faint afterglow permeating the entire universe. This expanding universe idea leads to a puzzle. What happens when things collapse inward? That's where black holes come in.
Black holes form when massive stars collapse at the end of their lives. During a star's life, there's a constant battle between gravity trying to crush it and the outward pressure from nuclear fusion in its core. When a massive star runs out of fuel, gravity wins, the core collapses. And depending on the star's mass, it can form either a neutron star or a black hole.
So a black hole is like this cosmic implosion where gravity is so strong that nothing, not even light, can escape.
Exactly. A black hole has a boundary called an event horizon, which marks the point of no return. Anything that crosses the event horizon is forever trapped inside the black hole.
It's like a one-way door to oblivion. But black holes are not just these static, empty voids. They have some incredibly fascinating properties.
One of the most interesting things is that black holes can rotate. If the star that collapsed to form the black hole was rotating, the black hole will inherit that angular momentum and continue to spin. This rotation can have some pretty wild effects.
Okay, I'm hooked. Tell me more about these wild effects.
Well, the rotation of a black hole can actually warp space-time around it, creating something called frame dragging. Imagine stirring a cup of coffee. As you stir, the liquid swirls around with the spoon. In a similar way, the rotation of a black hole drags space-time along with it.
So near a black hole, even time itself gets dragged around. That makes our earthly physics seem so simplistic.
Precisely. And it's not just matter that gets affected, even light itself gets twisted and bent as it passes near a rotating black hole. So black holes are not just these static, empty voids, they're dynamic and powerful objects that can warp the very fabric of space and time.
This is all so fascinating. But where does it leave us? We've talked about the Big Bang, the expanding universe, and these mind-bending black holes. What does it all mean?
Well, one of the things Hawking emphasizes is the quest for a unified theory of physics. A theory that can explain all the forces of nature, from gravity to the tiny world of quantum mechanics. We have separate theories that work well in their own domains, general relativity for gravity and the large-scale structure of the universe, and quantum mechanics for the subatomic world. But these two theories don't seem to play well together.
It's like trying to fit two different puzzle pieces that just don't quite match. But finding this unified theory is crucial for understanding the universe at its most fundamental level. Especially the very beginning of the universe, where both quantum mechanics and gravity played a key role.
Exactly. And while we haven't found it yet, there are some promising avenues of research, like string theory, which attempts to describe all forces and particles as vibrations of tiny one-dimensional strings.
String theory, that's a whole other deep dive. But it's exciting to think that we're constantly pushing the boundaries of knowledge and trying to understand our place in this vast and mysterious universe.
It certainly is. And in A Brief History of Time, Hawking doesn't shy away from some of the really big questions, like the nature of time itself. Why does time seem to flow only in one direction? Could we ever travel through time?
Right. He talks about this concept called the arrow of time, and it gets pretty philosophical. There's the thermodynamic arrow, where disorder or entropy tends to increase over time. Like a broken egg, you can't really put it back together.
Exactly. That's a great example of the thermodynamic arrow of time. And then there's the psychological arrow of time, which is our subjective experience of time moving forward, from past to present to future. We remember the past, but we don't know the future.
But wouldn't that make free will an illusion? That's a tough pill to swallow, even if it prevents paradoxes.
But that's a question that has puzzled philosophers and physicists for centuries. Hawking explores some mind-bending possibilities in the book, like wormholes, which are theoretical shortcuts through space-time.
Wormholes aren't those like tunnels that could connect two distant points in space-time, allowing for travel across vast distances, or even time travel. I've seen them in sci-fi movies.
Yes, that's the basic idea. Theoretically, a wormhole could allow you to travel vast distances in an instant, or even journey to the past. However, there are a lot of caveats.
Like what?
Well, for starters, we've never actually observed a wormhole. And even if they do exist, they might be incredibly unstable and dangerous to travel through.
I guess that's why we haven't had any visitors from the future popping in to say hello. But even if time travel were possible, wouldn't it create all sorts of paradoxes? Like, what if you went back in time and accidentally prevented your own birth?
Exactly. That's the classic grandfather paradox. Hawking suggests some possible solutions to these paradoxes, like the idea of consistent histories.
Consistent histories.
It's the idea that even if time travel is possible, the laws of physics would somehow prevent any paradoxes from happening. Everything would have to be self-consistent. You couldn't go back and change history in a way that would contradict your present reality.
So it's like whatever happened, happened. And you can't mess with the timeline. That's kind of a mind-bending concept.
It is, and it raises some profound questions about free will and determinism. Another idea Hawking proposes is the chronology protection conjecture.
Chronology protection, what's that?
It's the idea that the laws of physics would somehow prevent macroscopic objects like people or spaceships from carrying information back in time. So time travel might be okay for subatomic particles, but not for us.
There goes my dream of building a time machine. But even if we can't travel through time, just thinking about these possibilities expands our minds and makes us question our assumptions about the nature of reality.
It certainly does. And one thing that really struck me about A Brief History of Time is how Hawking connects these grand cosmic ideas to our own existence. We're made of the same stuff as stars, and we're here because of the Big Bang and billions of years of cosmic evolution. It's both humbling and awe-inspiring.
It really makes you appreciate our place in this vast and ancient universe.
Absolutely. And Hawking touches on the anthropic principle, which suggests that the universe is fine-tuned for the emergence of life.
So if certain fundamental constants of nature were even slightly different, life as we know it might not exist.
Precisely. For example, if the strong nuclear force were a bit weaker, atoms wouldn't hold together. And if it were a bit stronger, stars wouldn't be able to burn hydrogen.
It's like the universe is this incredibly delicate balancing act,
Yeah.
and we're incredibly lucky to be a part of it.
There's the weak anthropic principle, which simply states that we observe the universe to be the way it is because we exist. If it were different, we wouldn't be here to observe it. And then there's the strong anthropic principle.
What's the difference?
The strong anthropic principle goes further and suggests that there might be multiple universes, or multiple regions within a single universe, each with its own set of physical laws and constants, and we just happen to live in one that's conducive to life.
So there could be countless other universes out there where the laws of physics are completely different, and life as we know it couldn't exist.
That's one interpretation of the strong anthropic principle. It's a fascinating, albeit controversial idea. But even if we don't subscribe to the strong anthropic principle, it's still mind-boggling to consider how precisely balanced the universe seems to be.
It makes you wonder if there's some deeper meaning or purpose to it all, or if it's all just a cosmic coincidence.
That's a question that each of us has to grapple with on our own. But even if we don't have all the answers, I think it's important to keep asking these questions, to keep exploring, and to keep marveling at the universe and our place within it.
I agree. Hawking reminds us that the pursuit of knowledge and understanding is one of the most remarkable and rewarding aspects of being human.
It certainly is. And throughout a brief history of time, Hawking weaves in fascinating stories about the scientists who have shaped our understanding of the universe. It's like a history of scientific thought, from Aristotle to Einstein and beyond.
He talks about Galileo's struggles with the church, Newton's rivalry with Leibniz, and even Einstein's personal life and his views on pacifism and Zionism. It makes these scientific giants seem more human and relatable.
It does. And it reminds us that science is not just about cold, hard facts and equations. It's a human endeavor, driven by curiosity, passion, and sometimes even a bit of ego.
It also shows how scientific ideas evolve over time, with each generation building on the work of those who came before. It's a reminder that our current understanding of the universe is not the final word. There's always more to learn and discover.
Absolutely, and that's what makes science so exciting. It's a journey, not a destination. A Brief History of Time is a fantastic guidebook for that journey.
One of the things I really appreciate about Hawking's writing is how he brings in analogies and examples from everyday life to help explain these complex concepts. It makes it easier for non-scientists like me to grasp the essential ideas.
He does a remarkable job of making the complex understandable, like using a bowling ball on a trampoline to explain how gravity warps space-time. Brilliant.
He also has a great sense of humor, which keeps the book from feeling too dry or academic.
He does. And he doesn't shy away from using simple language. Even when discussing some of the most profound ideas in physics, he's a master of making the complex understandable.
It's a testament to his belief that everyone should have access to knowledge about the universe and our place in it.
Absolutely. And he leaves us with some profound questions to ponder. If we did find the ultimate theory, would it make the universe less awe-inspiring?
Or even more so.
That's the question. Would having a complete understanding of the universe diminish our sense of wonder, or would it deepen our appreciation for its elegance and complexity?
It's like knowing all the secrets of a magic trick. Does it make it less magical, or does it make you appreciate the skill and ingenuity of the magician even more?
That's a great analogy, and I think Hawking leans toward the latter. Understanding the universe doesn't make it any less amazing. In fact, it reveals even deeper layers of beauty and wonder.
It's like peeling back the layers of an onion, only to find that there are even more layers underneath each one, more intricate and fascinating than the last.
Exactly. Hawking points out that even if we did find the ultimate theory, it wouldn't necessarily mean the end of science. There would still be countless questions to answer about how the universe works on different scales, from the subatomic to the cosmic.
So it's not like finding the unified theory would be like reaching the summit of Mount Everest and having nowhere else to go. It would be more like opening up a whole new continent to explore.
Precisely, there would still be endless mysteries to unravel, endless possibilities to consider.
And who knows, maybe finding this unified theory would lead us to even bigger and more mind-blowing questions that we haven't even thought of yet.
It's certainly possible, and that's the beauty of science. It's a never-ending quest for knowledge and understanding.
Well, I think we've covered a lot of ground today, from Aristotle's insights to Einstein's revelations, from the expanding universe to the mind-boggling possibilities of black holes and time travel. A Brief History of Time takes us on an incredible journey through the cosmos.
It does, and it leaves us with a sense of awe and wonder. a deeper appreciation for the beauty and complexity of the universe, and a thirst to learn even more.
I couldn't agree more so. If you want to explore these ideas further, we highly recommend checking out Stephen Hawking's A Brief History of Time. It's a challenging read at times, but incredibly rewarding, and it might just change the way you view the universe and your place within it. Subscribe to our channel and purchase the book using the link provided